Hi, Year 11. So I'm just going to go through the first 20 multiple choice questions in this video from your mock. Sorry, it's a little bit dingy today, so the lighting's not great, but hopefully you can see everything that you need to. So what I've done next to each question is I've written down how many of you got this question right or wrong, so that you can kind of get a sense of how difficult the question was. So you can see that hopefully this one's quite easy. You are asked to find the volume of the block. So you know that a volume of a regular cuboid is just the base times the width times the length. So you're doing this multiplied by this multiplied by this value. So you can hopefully see that this length here is this one. 1 to 5 is 4 centimetres, so that's 4. You can hopefully see that this section here is this length. 4 to 11 is 7 centimetres. And then if this is the side piece, that is from 15 to 21, so that's 6 centimetres. And then you're just multiplying those together, and when you do that, you get 168 centimetres cubed, which gives you B. I have a funny feeling that we perhaps labelled this as 5 or this is 11 when we just plugged it straight in. So you've just got to check the start and the end point to get that right. So question 2 was done correctly by 85% of you, so not quite as well done, but still pretty good overall. So let's have a look at this one. You've got a measuring cylinder. You've got some liquid placed in there. That's 400 centimetres cubed is 400 millilitres. The total mass of the measuring cylinder and the liquid is 560. The mass of the measuring cylinder is 190. So the mass of the liquid must be the difference between the two. So that's 560 minus 190. And your so this is going to be the mass. You've got the volume here, so you can then work out the density of the liquid. So density of liquid is mass over volume. So the mass of the liquid was 560 minus 190, and the volume of the liquid was 400 centimetres cubed. And that gives us a value of 0.925 grams per centimetre cubed, and that's of the liquid. Okay, so then we place objects into the liquid, and the densities are given, and you have to state which ones will float. Okay, it will only float if the object density is lower than the liquid density. So you just need to look for the ones that are lower than 0.925. So obviously 1 and 2 are smaller, but 3 and 4 are bigger. So therefore it will be B. Okay, question 3 was good. 100% if you got this right, and it's just a memory thing. You just need to know it. A micrometer is used to measure very small lengths, the thickness of the sheet of paper. But the next one, number 4, was not done particularly well. So this was a momentum question and looking at change in momentum. So let's have a little look at what we've got. We've got a ball falling vertically to the floor, and it rebounds vertically upwards. So this is before, this is after the rebound. Just before it hits the floor, its speed is 4 meters per second, and after it rebounds, it's 3 meters per second. The mass of the ball is 0.5 kilograms. Right, so we know that momentum, P, is mass times velocity. So change in momentum, delta P, is going to be the final momentum, mv, minus the initial momentum. We'll call that mu, u for initial velocity. And I can just call that m brackets v take u. Now the thing to remember here is that momentum is a vector, so direction matters. Okay, so initially it was travelling down and finally it was travelling up. That's a direction change. So we're going to list down as being negative and up as being positive. We have to do that to take into consideration the opposite direction. Okay, so we're going to find our change in momentum here. Mass is 0.5. Final velocity v was +3 minus -4 is obviously 0.53 plus 4, which is 0.5 times 7. A half of 7 is 3.5. The unit is kilograms meters per second. So that tells us it's C or D. But we now need to think about the change in direction of the momentum. So initially it was falling down and it changed to be up. So the change in momentum is in the upwards direction, which gives us D. Number 5 was pretty straightforward. Again, it's just a memory one. Temperature in degrees Celsius is just a measure of the average kinetic energy of all the particles in an object, and that's energy is a scalar, it's not a vector. There's no direction associated with how hot something is, so that is B. Weight is a force, has a direction. Velocity is speed in a given direction. Acceleration is rate of change of velocity, therefore also a vector. Number 6 is looking at vector diagrams. So I'm just going to remind you, with a vector that we represent with an arrow, this is its top and this is its tail. Okay, if we are combining two vectors, tail to tail, we have to use the parallelogram method. So that means we draw construction lines that are parallel at each end of the vectors. If we have top to tail, like this, so you can see a top of a vector is meeting the tail of another one, then we can close the triangle. Okay, so we can see that we're looking at P and Q, and P and Q, these are the tails. Top, top, tail, tail, and it's the same for all of them. So they're meeting tail to tail. So to find the resultant of them, you're going to have to use the parallelogram method and not closing the triangle. So we can get rid of A and B straight away. Okay, so now what you have to think is, if you were to place an object here and take each force in turn, P would force it up to here, and then force Q would push it across to the right, and so it would end up here. Our resultant always starts from where the two initial vectors were joined together and end in that direction, giving us C. That was pretty well done by everybody. Okay, so now we are looking at motion. We've got a runner at 300 metres, runs 300 metres at an average speed of 3 metres per second, runs another 300 metres at an average of 6. What is her average speed for the total distance? So average speed is going to be total distance divided by the total time taken. Okay, in order to find the total time, we need to find the individual times. Okay, so if we use our speed, distance, time equation, time is distance divided by speed. Okay, so we're going to do 300 over 3, and we're then going to do, for the second section, we've got 300 over 6. Okay, so obviously we've got 100 seconds for this one, whereas we've got 50 seconds for this one. So we know that the total distance is 600 and the total time now is 150. We add them together. Okay, so we've got 600 over 150, and that is going to give us our final answer of 4 meters per second, which gives you B. Okay, number 9 then. This is again just one where you have to remember the basic equation and go from there. So mass and weight are linked. We know that the weight of an object, W, is equal to the mass of the object multiplied by the gravitational constant, acceleration due to gravity, which is 10. Okay, so W is 10 m. So we know that whichever row is right, the weight value is going to be 10 times larger than the mass value. Okay, so we can automatically get rid of C and D because these are smaller, not bigger. Both of these are factor of 10s greater, so that's fine, but now you need to look at the unit. We know that weight is a force due to gravity, and forces are measured in newtons, whereas mass is kilograms, giving us B. Number 9 was great, 100% if you got that one right, so well done. You know that if you're looking for acceleration, the gradient of a speed-time graph is acceleration, and the gradient here is constant, so therefore it is D. Okay, number 10 is about moments and equilibrium. You've got a metal plate with 4 parallel forces acting on it. Which one is in equilibrium? So we firstly need to define that. It means no resultant force and no resultant moment. So turning effect. Okay, so if we look at this, we can automatically discount D because the total to the right is 4 newtons and there's 3 newtons to the left, and they're imbalanced, so we can get rid of that. In all of the other cases, we've got 3 newtons to the right and 3 newtons to the left. So we have satisfied that there is no resultant force in A, B and C. But what we have to then look at is the turning effect of the forces. Okay, so if I place a rotational point in the middle of each, and I draw a line that is at 90 degrees to the direction of the forces, because moments are force multiplied by perpendicular distance to the pivot, or the turning point, what we can see is that we have moments set up that are different in size from each of these. So we know that we have a net turning effect because the 2 Newton force values are not acting along the same line. Okay, and so this 2 Newton force creates a moment that goes anti-clockwise, as does this one. Okay, this force multiplied by this distance, going to turn it this way. Okay, now that means you get a net turning effect, and it's going to be the same for the ones as well. Okay, whereas on C, which is the correct answer, this 2 Newton force multiplied by this perpendicular distance is going to try and attempt to turn the box around anti-clockwise, whereas this 2 Newton force multiplied by the same distance, so we know the size of the moment is the same, is going to try and turn the box this way. So these counteract each other rather than add up. So we get the answer is C. We don't have a turning effect and we don't have a resultant moment. Okay, so a boat is travelling at a steady speed in a straight line in question 11. It wasn't done too well. We got 55% correct here. So let's have a look. Steady speed means that acceleration is 0 meters per second squared. Okay, now we know from Newton's laws of motion that for an object to change direction or change speed, there has to be a resultant force. But if we have an object that's either stationary or at a steady constant speed, the resultant force is 0. Now the easiest way to think about this is we know that F equals ma. Okay, if we have a steady speed, there's no acceleration. So this is 0, so this is 0. The resultant force on the boat is 0 at a steady speed. Okay, number 12. So this is another moments question. You've got a handle with 3 forces, each 100 newtons applied to it. The handle is free to move. What is the effect of the forces on the handle? Okay, so here's the pivot point. The perpendicular distance from this 100 Newton force to the pivot is 0 because it acts through the line. There's no distance that's perpendicular for that force. So this one does nothing. Okay, I am going to call the distance on this side to the pivot, remember it's the perpendicular distance, I'm going to call that one y, and I'm going to call this one x. Okay, I'm going to call it anything, I'm just making up letters here. So we can see that we have the same size force, but they are clearly acting at different perpendicular distances to the pivot. Okay, now we know that a moment is the force multiplied by the perpendicular distance. Just being lazy and writing perpendicular by showing a right angle. Okay, so we can see that this 100 Newton force is going to be causing an anti-clockwise moment, whereas this one, pushing this way around the pivot, provides a clockwise pivot. Okay, so we know that for this moment here, this force multiplied by this distance, we've got 100y is clearly larger than 100x. Okay, because y is larger. So the anti-clockwise moment is larger than the clockwise moment, and so obviously it will then turn anti-clockwise, and that gives us C. Okay, question 13. We really struggled with this one as well. So a mercury barometer is a way to measure atmospheric pressure. So you have a dish of liquid mercury. You have a glass tube that is closed at one end and open at the bottom. This is a vacuum in here. This is evacuated. So this is air around the outside. Okay. So obviously air molecules are flying around and they push down on the liquid mercury with some pressure. Okay, because they hit with a force and it's over an area. Now obviously if the pressure of the air goes up, that pressure pushing down the force per unit area on the dish of mercury increases, and so there's nowhere for it to go but up the tube. Okay, so when the atmospheric pressure increases, this level of the mercury line goes up. Now what we know is that we can use the pressure equation. Pressure is rho g h. Okay, that's the density of the liquid mercury. G is just 10, it's a gravitational constant, and h is the height difference between the level of mercury in the dish and the level at the top. And so we're going to use that 75 centimetre value because we're finding the difference. Okay, we'll go back over pressure, I think, at some point when we're revising, because I think that might be helpful for you. Okay, 14. A man stands on the ground. What action will increase the pressure that the man exerts on the ground? All right. So we know that pressure is force over area. And it's a man standing, so the force is the man's weight. So that's the weight of the man. Over the cross-sectional area that he has in contact with the ground. Okay, so clearly if he's initially stood on the ground, his cross-sectional area is the sum total of his feet. If he raises his arms, that doesn't change. Okay, so it's definitely not C. If he bends his knees, the area that is in contact with the ground doesn't change, so it's not A. If he lies down on the ground, his cross-sectional area suddenly goes absolutely massive. Okay, if the cross-sectional area gets bigger, this whole thing gets smaller, but we're not looking for that. We're looking for the thing that increases. Okay, and so if he lifts 1 foot off the ground, his area in contact is now smaller, so this whole thing is now bigger, so it's D. 15 was done really well. You can see that 100% of you got this right. We know that temperature is a measure of the average kinetic energy of the particles. So if they are travelling at a higher speed, they are going to hit the sides when they collide much harder. They've got a higher velocity. So that one was B. 16, we need to do a little bit of work on for some of you. So this was Hooke's law. So you can see, let me just move this in a little bit, sorry. A steel spring, graph of length against the load applied to it. So the first thing we're going to do is write down Hooke's law. So F equals Kx. So this is the force on the spring constant, X is the extension of the spring. Okay, in order to find the extension, we need to know its original length before any loads were added. So we can see that when the load was 0, nothing was added, the original length was 5 centimetres. That's our first thing to look at. Then it says, what is the extension of the spring when a load of 20 newtons is applied to it? So we check at 20 newtons, and you can see that the length was 8 centimetres. But 5 centimetres of that is just its normal length. So it's the difference between the two. 8 minus 5 gives me 3, gives me A. Okay, 17, again, is just about remembering your energy resources. So nuclear fission generates electricity by boiling water, because basically the nuclear reactor gives off loads and loads of energy, but that needs to be channeled in a certain way basically. So we take a huge amount of water, the energy that is generated from the fission reaction heats the water up, turns that to steam, which then turns a turbine, which then works with a generator. Okay, with A, C and D we already have movement of water, so we already get the movement. We don't need to boil it, we just need to turn it into steam to create that movement with fission. Number 18 is looking at energy changes. So we've got a car, it's a flat, that's not the question, is it? Sorry, not paying attention. Here's your flat road. Okay, flat and horizontal means that the vertical height change is 0. Okay, so h is 0 vertically, and gravitational potential, which is mgh, will therefore be 0. So it is clearly B. Obviously the chemical energy of the fuel is going to change, because we burn fuel to transfer energy so that we can gain kinetic energy of our car. The internal energy of the engine will get hot. You must have felt a car bonnet at some point after it's been driven. You want to be careful with that, don't want to burn your fingers, but yeah, cars get hot when they are used. And obviously the kinetic energy is changing because it starts and stops several times. So that one should be fairly straightforward. Okay, 2 more in this video then. So only 20% of you got this right, so I think this might be the worst question on the paper. So let's have a look at this in a little bit more detail. We've got a steel ball fired vertically up with a velocity v, and it reaches a height h. Okay, let's try and draw this in. So here's the ground. The ball is fired up and it reaches a height h. It initially had a velocity of v. Initially, the ball had kinetic energy, which is a half mv squared. Because I'm told that air resistance can be ignored, there's no heat loss to the surroundings or sound loss. So I can say that all of the kinetic energy at the bottom is transferred to the potential energy at its highest point. Okay, there's a conversion between the two. So I know that my half mv squared is converted into mgh. Okay, now I then do this again. It's the same ball, so it has the same mass. Okay, so the mass is constant. A half is constant because it's just a half, and g is just 10. So the only things that are different now are the original velocity v and therefore the height that we reach. Sorry, it comes a little bit blurry, but hopefully it's still clear enough to see. Okay, this time it had a velocity of 2v. The kinetic energy is now a half m, same mass, but this time it's 2v for its velocity squared, which is a half m 4v squared. So you can see that the kinetic energy for this one is 4 times larger. And so the height that it reaches, its new mgh, if m and g are constant and the total energy is now 4 times bigger, the height has to also be 4 times bigger. And so it's C, 4h. Okay, last one on this video then is number 20. 50% of you got this right. So again, it was one that we struggled with a little bit. So it's looking at power and efficiency. So, let me zoom out just a little bit, sorry. We've got a motor is used to lift a load of 40 newtons and it's lifted through 0.5 meters. So the first thing I'm going to work out is the work done. The energy transferred is force multiplied by the distance travelled in the direction of the force. Okay, so 0.5 multiplied by 40. Okay, so in order to raise this 40 Newton load by 0.5 meters, I have to transfer 20 joules to it. I have to do that, otherwise it will not reach 0.5 meters up. The power of the motor is 40 watts, but the system is only 20% efficient. So it only transfers 20% of the total energy to useful energy. This is clearly useful. I'm trying to lift it up. Okay, so 20 joules is only 20% of the total energy that we have to supply, because 80% of the energy supplied by the motor is going to be wasted. Okay, if 20% is 20, 10% is clearly 10. We need another 80% to get the total energy. Okay, so 80% is wasted energy, but we still require it to get the 20% that is useful. That's clearly going to be 80 joules. Okay, so actually, in reality, although the gain in potential energy is only 20 joules for this load, it actually requires 100 joules So the total energy required is the useful and the wasted. So 20 plus 80 is 100 joules required. So this is the useful work done. This is the total work done. And so now we can find the time, because we know that power is energy over time. We can rearrange that, and we're going to do energy over power, which is the work done divided by the power, which is 100 over 40. 10 over 4 is 2.5 seconds, which is our final answer there. Hopefully that helps a little bit with 1 to 20, and I will do a second video for you shortly.